If you work with AI, machine learning, graphics, games, data science, or even search engines, you constantly hear the word vector. Embeddings are vectors. Positions are vectors. Gradients are vectors. Images can be vectors. Ask a developer what a vector is, and 99% of them will tell you. It's an array of numbers, or maybe an arrow pointing in space. But mathematically, that is only half the truth. A vector is not necessarily an arrow. It is not necessarily an array of numbers either. A function can be a vector. A matrix can be a vector. Even a polynomial can be a vector. So what exactly makes something a vector? The answer is not its appearance. The answer is the system it belongs to, vector space. To a mathematician, a vector space isn't a data structure. It's an interface. It is an API contract. And once you understand what this interface actually requires, it will completely change how you think about AI, machine learning, and data architecture. Developers often use vectors without needing the formal definition. That works, until it doesn't. You may add two embeddings and assume the result represents a meaningful concept. You may normalize vectors and assume the normalized results still form a vector space. You may treat RGB colors as vectors, even though valid RGB colors are not closed under normal vector operations. Understanding vector spaces helps you know which operations are mathematically valid, what structure your data has, and which assumptions your algorithms depend on. In software, an interface doesn't care about the underlying data. It just cares about behavior. A vector space operates the exact same way. It doesn't care if your data is an array of floats, a 3D coordinate, an RGB color, or a continuous function. To be a valid vector space, your objects just need to implement two specific methods of a specific interface. Interface vector space of T has two methods. Vector addition, add vector 1 and vector 2. The result must be a vector of the same type. Scalar multiplication, multiply scalar with a vector, and the result must be a vector of the same type. That's it. That is the core of linear algebra. First, addition. If you take two objects in your space and add them together, you must get a new, valid object of the exact same type back. Second, scalar multiplication. If you multiply your object by a regular number like 2 or -1, it stretches, shrinks, or reverses, but it remains a valid object in your space. But simply implementing these methods is not enough. They must behave according to the following 8 rules that are familiar to any developer. Commutativity of vector addition. Vector A added to vector B is the same as adding vector B to vector A. Associativity of vector addition. Adding 3 vectors A, B, C is the same no matter the order you start the addition with. Additive identity. Adding vector A to a vector 0 outputs an identical vector A. Additive inverse. Adding vector A to its opposite will result in vector 0. Multiplicative identity of scalar multiplication. Multiplying 1 with vector A results in vector A. Associativity of scalar multiplication. Multiplying scalar y with vector A, then the result with scalar x, is the same as multiplying scalar x with vector A, then the result with scalar y. Scalar multiplication distributes over vector addition. Adding vector A to vector B, then multiplying the result with scalar x, is the same as multiplying vector A with x and vector B with x, then adding the results. Scalar addition distributes over scalar multiplication. One of the most important requirements is called closure. Closure means that when you apply an allowed operation, the result stays inside the same set. Take valid RGB colors. Add them. The result is outside the valid RGB range from 0 to 255. So valid RGB colors do not form a vector space under ordinary addition. Looking like an array of numbers is not sufficient. Now consider all pairs of real numbers x, y. Take any two vectors, add them, multiply by any real number. The result is always a pair of real number, which means it stays in the same set. There's a 0 vector, and every vector has an opposite. So all pairs of real numbers form a vector space. The same is true for arrays of 3 real numbers. 1,000 real numbers are millions. That is why embeddings usually live in spaces, such as are with dimension 768 or higher. Why do we care? One word, polymorphism. Mathematicians have spent the last 200 years writing algorithms for vector spaces, finding the shortest distance between points, calculating angles, compressing data. If your objects implement the vector space interface, you get all of those algorithms for free. This is the entire foundation of AI and large language models. Calculate similarity is a function that takes two vectors as inputs, compute their dot product, and divide by the product of their magnitude or length. This function doesn't know if it's comparing two English sentences, two user purchase histories, or two pixels on a screen. That is the magic of abstracting math into an interface. And this is the strong point of developers. Do you remember when you created an abstract class called vehicle to represent cars, trucks, bus, tractors, etc.? Now, for the mind-bending part. A vector is not defined by being an array. Consider two functions, f(x) and g(x). We can add them. We can scale one. There is a 0 function, and every function has an additive opposite. Under the right conditions, functions form a vector space. The same can be true for polynomials and matrices of fixed size. This reveals the deeper definition. A vector is an element of a vector space. It does not need to be an arrow. It does not need to contain coordinates explicitly. Its behavior under addition and scaling is what matters. Have you ever mixed audio? An audio signal is just a continuous function of time. If you take a guitar track and a vocal track and play them together, you're literally doing vector addition. If you turn the volume knob down by half, you're doing scalar multiplication. Audio waveforms are vectors. Let's look at this equation. If f is a sine wave and g is a cosine wave, they are our fundamental building blocks, basis vectors. They act exactly like the x and y axis on a graph. So what are a and b? They are just the coordinates. The array a, b is not the vector itself. It's just the address telling the computer how to mix the true vectors and here the functions together. In software, because 3D coordinates map so perfectly to a 3-item array like x, y, z, we got lazy. We started calling the array the vector. But remember, the array is just a list of coordinates representing how much of each basis vector to use. Let's see a complete implementation of a vector space using TypeScript. This is where the abstraction becomes real, where the interface stops being theory and starts being something you can actually run. We begin by defining the interface itself. We'll call it VectorSpace and give it a generic type t. This interface declares exactly 3 things. First, the 0 vector, a function that returns vector that is 0, meaning it does not change the result of an addition. Second, the add function. It takes 2 vectors of type t and returns their sum, also of type t. Third, the scale function. It takes a scalar number and a vector and returns the stretched or shrunk result. 3 methods. That is the entire contract. Now the fun part. We provide 2 completely different implementations of this same interface. Not slightly different, fundamentally different, and yet both are perfectly valid vector spaces. The first implementation is vector 2D. It represents a point on a flat plane using 2 coordinates, x and y. For this space, the 0 vector is simply the point where both x and y equal 0, sitting right at the origin. The add function takes 2 points and adds their x coordinates together and their y coordinates together. The scale function multiplies each coordinate by the given scalar. Clean, straightforward, what you would expect from a 2D graphics library. The second implementation is function space. This one is less obvious. We start by defining a type called real function. It is any function that takes a number and returns a number. That is our vector type, not an array, not a pair of coordinates, a callable function. For this space, the 0 vector is a function that ignores its input and always returns 0. The add function takes 2 functions, f and g, and returns a brand new function. When you call that new function, it calls both f and g with the same input and returns their sum. The scale function takes a scalar and a function f, and returns a new function that calls f and multiplies the result by that scalar. Look what we just did. One implementation operates on pairs of floats. The other operates on functions from numbers to numbers. They share 0 lines of internal representation, and yet both satisfy the exact same interface. Same method names, same type signatures, same mathematical rules. This is polymorphism applied to linear algebra. Now, let's put this abstraction to the test with something practical. Something you have probably used without realizing it is a vector space operation. The lerp function, short for linear interpolation. Lerp transforms a source value a into a target value b, controlled by parameter t that moves between 0 and 1. When t is 0, the result should be pure a. When t is 1, the result should be pure b. In between, you get a smooth blend. Here is how it works under the hood. Lerp computes 1 minus t, scales a by that amount. Then it scales b by t. Then it adds the 2 results together. At t equals 0, 1 minus t is 1. So the first term is all of a. The second term is 0 times b, which disappears entirely. As t increases, we take a smaller portion of a and a bigger portion of b. The transition is seamless. By the time t reaches 1, 1 minus t becomes 0, a vanishes, and b remains in full. And here's the magic. This lerp function never asks what a and b actually are. It only needs the vector space interface. It calls scale. It calls add. That is it. Feed it a vector 2D space with 2 points, and it animates a character across a screen. Feed it a function space with 2 audio signals, and it crossfades between a guitar track and a vocal track. The lerp logic is identical. The implementations are worlds apart. That is the power of treating a vector space as an interface. As developers, we are used to separating the interface from the implementation. Once you realize that linear algebra is just the standard library for the vector interface, high-level math stops looking like magic. It's just polymorphism. Whether you are scaling an image, predicting a stock price, or building the next ChatGPT, you're just calling add and scale functions. So the next time an AI explanation says that concepts live in a high-dimensional vector space, you will know that this is not just a fancy way of saying a very long array. It means those representations live inside a system where linear combinations, transformations, distances, and directions can be studied mathematically. And that is the real foundation behind much of modern AI. If this clicked for you, hit subscribe. Let me know in the comments if you want a deep dive into how algorithms like PCA compress these dimensions to make AI faster. Keep coding, keep learning, and I'll see you in the next one.